Hi, I'm very happy to be here today with you for this session on biases in artificial intelligence. And we will see mainly how to detect them with some code and a demo. And to start with, we are going just to see some problems that we can have with biases in artificial intelligence. So my name is Mathilde Virginie. I'm French, as you can hear, maybe. I'm here with my colleagues. I work in teamwork. Thank you, guys. And I'm the manager of the modern data department. And so I've started artificial intelligence 19 years ago, when it was not cool to do artificial intelligence. And so I have seen some very interesting things since that time. So to start with, do you know that nearly every model in artificial intelligence has biases? Even models that you are using maybe on a daily basis or nearly, like, for example, Google Translate. So Google Translate has gender bias. For example, if you look at that, so it is a French sentence, un infirmier va à l'hôpital. If you translate it in English, you will have a nurse goes to the hospital. It is OK. And when you go back in French, you have une infirmière va à l'hôpital. And if you have seen what happened here, you have a switch between a male nurse and a female nurse, and the male nurse is now a female one. Google Translate is not the only one to have this problem. In fact, you can find this kind of problem in every translation engine. And if you use AWS Translate, for example, it is the same, and it is also the same for DeepL. So in DeepL, I have tried another sentence. Trois infirmiers et une infirmière vont à l'hôpital. In English, it is something a bit strange, but it's working. 3 nurses and 1 nurse go to the hospital. And if you go back in French, you have trois infirmières et un infirmier. And you have a switch. You add 3 male at the beginning and only 1 at the end. And you have 3 female at the end, 3 women. And you had only 1 woman at the beginning. And so it is a problem. It is a problem because, in fact, in most documents that you can find on the internet, there are more female nurses than there are male nurses. And so it is why translation engines are thinking that nurse, by default, is a female one, and they are not saying that to you. And so this is one kind of problem. Of course, it is not too important in that case. You can live with it. But it's important to know that this bias exists. So today, we will see what is a bias, or you can spot them in datasets and in models. And so we will do a little demo, and then I will finish with a wrap-up. So you have the QR code for the code, of course. If you want to download it, it is a GitHub repository. So you can go in it, you can download it, and use it when you want. You will receive the slides at the end. So if you don't have the time to take the QR code right now, it is not a problem. You will have it after that. So what is a bias? A bias is an inclination or prejudice for or against one person or group, especially in a way considered to be unfair. What is important is that in artificial intelligence, when you have biases in models, the model will do more mistakes for some people, for a group of people, than for the other ones. So the model is maybe working very good in most cases, but maybe that for some kind of people, it will not work at all. And this is a problem because it is most of the time for the minorities group, and it will not work for the minorities. And this is important. And it can be very, very dangerous. For example, in the past, there was the Uber car. And the Uber self-driving car has killed someone. It was a woman, late. She was going home with her bike. She was walking near the bike, and she crossed the road in front of the car. And the car didn't see the pedestrian crossing the road. And so the car didn't brake, and the woman was killed with this accident. So this is very important to be sure that you have not this kind of biases. And they have tried to figure out why the car didn't see the pedestrian. And they have worked a lot of time on that, and they discovered that, in fact, the problem was that she was not crossing on a pedestrian crossing. And so she was jaywalking. I'm not an English speaker. I speak English, but I'm French, so I didn't know the jaywalk word. And it means to cross the road outside of pedestrian crossing. And so in French, we just say traverser, because we do that all the time, in fact. So if the Uber car was in France, I think they would have found this bias very quickly, maybe just after the first try, but not here. And so they have killed someone because in the data set, when they have trained the model, there was nearly no pedestrians crossing outside pedestrian crossing. So if no one was jaywalking, the model has learned that pedestrians are people on pedestrian crossing. So this is a problem. And of course, the data scientists of Uber haven't said, oh, I don't like jaywalking. And if we try to kill everyone that is jaywalking? Of course not. They didn't mean to put this bias in their model. They don't even think about it. And it was after the kill that they have said, oh, maybe we have made some mistake somewhere, and maybe we have not seen that there was a bias in our model. And so most of the time, in 99.9999911, biases don't come from the data scientist, they come from the data set. And so your main task as a data scientist is to study the data set to find these biases, to remove them, and then to train your model with a good data set. And we will do a little game. So I will show you a data set, a very simple data set of carrots. You know what is a carrot, I think. So I will show you a data set of carrots. You will have 15 seconds to find biases in my data set. OK? This is the data set. This carrot doesn't exist, in fact. It is created by an AI, which is DALL-E. It is an open AI art generative model. And so I didn't take any real photos. So these are carrots. Have you spotted some biases? We will see them, and we will see if you have them. In fact, I have found 3 biases. The first one is that the carrots are cleaned. Every time in my data set, they are very clean, with no soil and nothing else. But carrots are not growing in the air, so they cannot be clean every time. The second one is that every carrot in my data set is straight, but carrots are in all sizes and forms, and so you can find some ugly carrots like that. And in fact, it's all that I have in my garden. I'm trying to have straight carrots, but I don't know how to do that. So if you know, you can come at the end and tell me that. And the last one is that carrots come in different colors. So there is diversity in carrots, and they are from white to purple. Of course, you know the orange ones. They are the most common ones, but they are not the only ones. Who in this room has found these 3 biases? No one. Who has found at least 1 bias? Exactly. A lot of people has found at least 1 bias, but no one the 3 of them. So if you want to work on biases, oh, sorry. I've got other biases. They are not the only ones. I agree with you. So if you want to detect biases, you will have to have a whole team to do that, because you have bias. And if you want to remove them from your data set, you will have to work with a team to find all of them. So now we will do a little demo to know how to do that in a real case, not in a carrot dataset case, even if I love the carrots and my carrots dataset. So we will switch to the demo. I will try to do that. Wow, it's working. Well, there is a big button with a tag, demo, on it. So it's not that difficult. So what are we going to do? We are data scientists, and we want to do a very good thing for humanity. And so we are just looking at what may lead to death in the world. And so, as you can see, the leading causes of death, they are the 10 first. It was in 2019, so there is no the COVID in this one. It is something like the 5th or 6th for the COVID. So the first one is heart disease. If you want to save a lot of people, you will have to do something against heart diseases. So it is what we are going to do, or trying to do. And we are trying to do a model that will spot who has a high risk to have heart disease, because most of the time, if you die from a heart disease, it is because it was not diagnosed before. So we will try to help people to know if they have a high risk to have a heart disease or not. Okay? So the project seems very interesting. It seems statistical. So we will use a data set that was found on Kaggle, if you know the website. It is the personal key indicators of heart disease. And it is a survey from the CDC, so done in the US, and with 400,000 Americans. So it is a big data set for health issue, because in most cases with health, you have small data sets. And so we will try to find biases in our data set, and then to train models, and to be sure that our models are not biased, so that we can use them to save a lot of lives. Okay? If you're working in data science, you know that we work with an iterative process. We use the CRISP-DM methodology, but there are other ones, and there are different steps. You are going on the steps until the model is good enough to go to deployment. And so you start with business understanding. The goal is to discover what the customer really wants, what are the data, where they come from, and so on. Then you do the data understanding. You will study the data set. The data preparation step, so you will do what is needed to have a beautiful data set. The modeling, the training step, and an evaluation step to see if everything is correct. And we will be able to spot biases in 3 places: the business understanding, the data understanding, and the evaluation steps. So we will go from one to another and see what we can do at each step in this case. Of course, as I want to show you some biases in the models at the end, I will not remove the biases that we will find in the 2 first steps, okay? So we will just look at them and say, okay, here there is a bias. Here what is you can do to remove them, but we will not remove them. We will keep them. There is a lot of text, as you can see, in the notebook. It is because you will be able to download it from the GitHub repository, and maybe you will not remember everything that I have said or things like that. And so there is a lot of things in it. I will not show you everything because I don't have the whole afternoon to do that. So I will just pick some interesting information in it, and you will be able to see everything when you will have the time to do that. Okay? So if we look at Kaggle, what it said for the business understanding part, it said that originally the data set comes from the CDC. which conducts annual telephone surveys to gather data on the health status of US residents. Then you have some numbers, and so at the end, I decided to select the most relevant variables from it and do some cleaning. Okay, when I read something like that, I see some red flags, a lot of red flags. So I know there will be biases in my data set. They are fun survey. Do you answer fun survey? Who is answering fun survey in this room? No one? Not even one people? No? Okay. So you're not in the survey, you're not in the data set. Who will answer this kind of survey? People who are mainly not working, who are staying home, but are not too poor to have a phone line, because if you don't have enough money to buy food, you will not buy a phone line. So you don't have, in fact, something that represents the whole population. Second, it is done in the US, so you have only US citizens. Maybe health in the US is not exactly the same than in other countries. And the data set has been cleaned. It is the last sentence. I decided to select the most relevant variables from it and do some cleaning. But you do not know what choices were made and which preparation step. What was the preparation that was made in this data set? We don't know. So there are a lot of problems, and moreover, it is not a clinical or hospital data set. It's just a phone survey, okay? So I know that if you look after that at some questions that were asked, maybe you would have lied. So the second phase is to look at the data dictionary. So for each feature, we have the descriptions. I'm sorry, I cannot grow the text bigger for this array. We have the format, the unit, and some comments. And for example, the second feature is the BMI, body mass index. It's saying if you're underweight, if you're normal, overweight, obesity, severe obesity, things like that. Do you know your exact weight? No, maybe not. I know my exact weight because I'm on a diet, and so I'm not the only one, as I can see. But in most cases, you don't know your exact weight. And maybe you don't know how to compute your BMI, okay? And if I ask someone what's his weight, maybe he will not say the exact number. If you ask me what's my weight, first I will think it's very rude. And second, I will not say I think the real number. I will be a bit more like, oh, well, it's nearly 60. So this feature is not very good one, and you don't know if it will be exactly the real one. There are some things that are more interesting ever. You have the alcohol drinking. Are you a heavy drinker? And the definition is that a heavy drinker, if it is a man, is someone who is drinking more than 14 glasses of alcohol by week. For a woman, it is 7. Who is a heavy drinker here? Oh, surprise, no one. Oh, one. Very brave. Of course, if someone is asking you by phone if you're drinking, if you're a heavy drinker, most people will say no, no, no. So it's not a good feature because we know that there may be some problem with that kind of feature. Of course, you have other things like that. We have some problem between sex and gender, but it is in most data sets. And you have some things like, on average, how many hours of sleep do you get in a 24-hour period and things like that. So what I have seen just regarding the source of the data set and the feature definition is that there will be many biases in this data set. I know that. I will show that there are many biases after that. And so in the first step, the business understanding step, you know if there will be some problems or not. Maybe you will not see the problem at that step, but you may find some problems even before looking at the data. And so it is the first interesting step. Stop. Think about your data set. And will there be some biases or not regarding the source, regarding the feature definition? Once you have done that, you can go to the data understanding step. The data understanding step is the second one. You will have to study the data. So I have just run the whole notebook just before. So there are a lot of imports and things like that. I'm loading the data set, so the loading is correct. I will do some data set splitting between train and test. It is very important. Never work on the whole data set, please. Only on the train one. But I've seen a lot of people doing that on the whole data set, and each time it's difficult for me to see that. And then we will do some statistics. The first statistics are univariate analysis. This means that you will look at each feature one by one and see if there may be some problem on that. For categorical feature, it is very easy. You are trying to find a well-balanced distribution, something that is very uniform between every modality, and you understand every modality that you have, and you have no missing value, so something very classical. If we look at the target feature, which is the heart disease, we can see that. I was searching for something very balanced, very uniform, and I've got that. 91% with no heart disease, and only 9% with heart disease. I know my model will not work very well with this kind of distribution. So you can do a lot of things. You can do oversampling, downsampling, subsampling. It depends on how you want to tell them. You can grab more data in order to have more yes category, not no, because you have too much of them. But you will have to do something, because right here, if I do a very dumb model that is saying that no one has heart disease, I've got 91% accuracy. So my accuracy will be very high with a model that is very poor and that is useless. So be careful with this kind of things. Try to have something that is a bit more balanced. We will look at the diabetic feature. And if you are trying to do some description, or if you're plotting it, the question was, do you have diabetes? So the answers are yes or no. And in fact, you have 4 modalities. Yes, no, and 2 other ones. There are yes during pregnancy. It is a specific form of diabetes, and no borderline. So you don't really have diabetes, but you may have in the future. You don't know what to do with these 2 modalities. And when you have extra modalities, it's always a problem to know what to do with them. If you remove the yes during pregnancy and a no borderline, you remove a whole range of population. And so you have to ask experts to do that and to say, okay, what can I do with them? I cannot create a model for them because there are too few of them. If you look at the pie chart, there are really few yes during pregnancy. They are the red ones, and no borderline. They are the green ones. And so you cannot keep them like that. So there are no solution that you will be able to use every time. You will have to think about that, and what can I do with them? Here we will do something very simple. The yes during pregnancy will go in yes, and the no borderline will go in no, but it was my choice. I think it's not the good one. And if we are looking at something like the race, you have 6 modalities: white, Hispanic, black, other, Asian, and American Indian and Alaskan Native. And you have this kind of distribution. Remember, we are trying to have uniform distributions for categorical features, and it's not the case here. What can we do with that? There are too many white people in my data set, so it can work for minorities. Maybe I can do subsampling in the white class, or maybe that's something that's working in a lot of time. I can create two models, one for white people and one for other people, and the second one will manage diversity. So the white model will not manage any diversity in it. It will be only for the white. And for all other people, I will create a real model that is working for them regarding the distribution, because they are more balanced for other people than for white people. So it may be a solution to create many models in some cases and not to create one model for everyone, because one size fits all doesn't work in practice in a lot of cases. For the numerical feature, you are trying to find either uniform distribution or a Gaussian one, a very good Gaussian distribution. And so you can study them, for example, with the BMI. So if you just look at the statistic, the BMI here is from minimum 12 to maximum 19.4. You are in the normal category for the weight if you are between 18 and 25. 25 to 30, it is overweight. 30 to 35, it is obesity. More than 35 is severe obesity. And we have someone with 94. So if I was with a BMI of 94, I have done the computation, I will weigh 258 kilos, but as we are in the US, it is 567 pounds. So a lot, okay? So we have people with very, very high BMI in the data set. And if you look at the distribution, you will have something like that. So it is very skewed. We have a lot of people in the normal range, but we have some people with very high BMI. They are outliers. Statistically, they are outliers. But if you remove outliers, your model will not be able to understand what to do with people with a high BMI. And you cannot just say, oh, there are more than 3 standard deviations from the mean, so I just remove them. No. In this kind of cases, you cannot keep the numbers. There are too few high numbers. You cannot just remove them. They don't exist. They will be very happy to know that. So one thing you can do is feature engineering, creating a new field, which will be a categorical in this case, from this numerical feature, and with no or less biases. So here you can use the definition of the BMI classes. You are underweight if you are under 18, normal between 18 and 25, overweight 25, 30, and so on. And so you will create a distribution that will be more uniform. And every people with severe obesity will be together. And you will keep them, and it will work for them. Physical health is very strange. It is a feature that is saying, in the last 30 days, how many days were you physically ill? So it is something between 0 and 30. 0, you were okay the whole month, and 30, you were ill the whole month. And we have this kind of distribution. So I'm trying to have uniform distributions or Gaussian ones, and here I have something that is not even a distribution, in fact. There's a lot of 0, and some other people in the other cases. You don't even see where the people with a non-zero value are, so you can just remove the 0 to see the distribution for people from 1 to 30. And you see that there are some very strange things with peaks at 2 weeks, 3 weeks, and things like that, because it is easier to answer 2 weeks, I was ill 2 weeks during the last month, than 12 days exactly. And you will not be able to use that kind of field, because with this kind of feature, you will have biases at the end, because maybe because there is only one people with 17 days sick, the model will learn that for 17 days, exactly 17, you can say that you will have or not a heart disease regarding the only people you have in this category. So you cannot use that. It will be biased. And so what you can do here is just to create a flag saying if it is 0 or if it is non-zero. You will lose a bit of information, but you will be able to use this feature. It's better than to just delete it. You have the same with the mental health. And sleep time is very funny, because sleep time is the average number of hours you are sleeping every night. And if you look at that, you can see that the maximum for the dataset is 24 hours. So someone in the dataset is sleeping, in average, 24 hours a day. In average. So maybe some days he's sleeping 26 or 27 hours a day, I don't know. And I don't even know how this person has answered the phone survey, because the person was sleeping during the call. So I don't know if there are some funny guys saying things that are not real, just to say, oh yes, I have answered the survey, I have 5 minutes to do some things, I have the phone call, okay, or they have given the phone to their child, saying, oh, you can play with it, answer it. Because 24 hours, it's a bit strange. So I think there are some problems in this feature. And you have this kind of distribution, of course. Most people are sleeping between 5 and 10 hours a day, so it's a good thing, but it is not really a Gaussian, and you have something very strange with the 24, 23, 21 hours of sleep in average by day. So maybe you will not be able to use it either, and maybe you will do categorical feature with that, saying that they are sleeping not enough, they are sleeping enough, or they are sleeping more than what we are told to do. I know I don't sleep enough, for example, because I think you have to sleep 8 hours in average by day, and I don't think I sleep 8 hours a day, but I have a child, so it's very difficult to sleep with children. So you have to do that for every feature that you have in your dataset. Here I had 18 features, and I have shown you maybe 6 features. So of course, it will take a lot of time to do that for every feature, but it is very important to do that for every feature you have. So if you have 2,000 features, it will take a very long time. Maybe you can take some interns to do that. When you have done the univariate analysis, you will do the bivariate analysis, meaning that you will study 2 features together to see if there is a link between the 2. If you see a correlation between 2 features, it can be either a very dangerous bias or a very interesting insight. And you don't know if it will be very dangerous or very interesting if you are not looking exactly at what happened here. So you cannot use a tool who will say, oh, this is dangerous, this is very interesting. The only thing that can do that is human intelligence. So you will have to think about it and say, okay, is it normal or not? And how to see if there are some correlation between features. If the 2 features are numerical, it is very easy. You have just to do a correlation matrix. And with a correlation matrix, you have something like that. So you have the numbers right here, and you have something more graphical after that. And you see that here in my dataset, there are not a lot of correlation. So it is a very good dataset for this point. The most correlation is of 0.0 0.29, it's not that much. We are thinking that the high correlation is something that is higher than 0.8 or 0.9, so here we are okay. If you want to be sure that it is not a very important bias, you can do scatter plots, but here if I do the scatter plot, I will see that. Because I have numbers between 0 and 30 for both feature, and when I plot them, I don't see anything because there are some plots everywhere. What I do when I have that is that I just add a little random bias on my data, a little noise, to see something that is more like that. It's the same data set, but adding a little noise, random noise, you will be able to see if there is something, and I can see that there are some correlation, but they are not that important, so I will say that it is correct, and I can keep them. You add two numerical features, it's easy. If you have a numerical feature and a categorical one, you cannot use a correlation matrix. So what you can do is you can create some box plot and see if the distribution is the same for every category, for every modality in the categorical feature. Here, for example, we can see the heart disease. Do you have an heart disease or not? Regarding the BMI. And what we can see is that when you have heart disease, you have a similar distribution than when you don't have an heart disease. So in this plot, I cannot see a lot of differences between the both of them. It is just slightly less in the array for people without heart disease, but you cannot say there is a correlation between the two of them regarding just that. If we look at the physical health, here we can see a correlation because the two distributions are not the same. For no people, no heart disease, most of the time they are not physically ill. But for people with heart disease, they are more ill during the last month. So it is something that you can see to find correlations. And after that, you have to think, is it a good correlation? Is it an insight? Here it is an insight. Or is it a bias? Of course, we think that the more you are ill and the more you may have an heart disease, seems to be a very good insight. And if you have two categorical variables, you can use Mosaic plots. There are plots that I use a lot because I like them. They are very graphical. It's very easy to spot things. And so what you are looking are areas representing the people in the data set. So here I have the sex, the gender, but it is named sex in the data set, female and male. And for every modality, you have with heart disease or without heart disease. And what I can see is that for male people, there are slightly more heart disease than for women. And it is an insight that is very interesting because we know that. And if you look at scientific papers, you will find that women have less heart diseases than men. So there is a correlation. Small one in this case, but it is a normal one that you have to keep. If you do the same for alcohol drinking, you will have something that is very different. What you can see is that there are more people with heart disease in the non-heavy drinker than in the heavy drinker. Remember, I have said that alcohol drinking may be a bit biased because a lot of people will lie. And here we can see that the more you're drinking, the less heart diseases you will have. So if you just train a model on that, the model will say, drink alcohol. In France, we say that you have to drink 1 wine of alcohol by day to have no diseases at all. It was, until maybe 20 years ago, it was very often that you can hear such sentences. But now we know it's not the case. And we know that drinking alcohol and drinking a lot of alcohol is not a good thing and you will have more heart diseases. But it's not the case in my dataset. And here, I don't have an insight. I've got a bias, a very dangerous one who will taught people to drink alcohol. So don't drink too much alcohol, even if the graph is saying that you will have less heart diseases. Please. And so you are doing that for all the features that you can cross 2 by 2 to see if there are some insights, some biases, and so on. At the end of the data understanding step, you have looked at every feature individually and crossed with another one. So you have a good view of biases, and you have said for every feature what you can do. Do we have to remove the feature? Do we have to keep the feature? Do we have to create feature engineering? Do we have to subsampling, to do oversampling, and so on? So at the end of the data understanding, you have a list of action to do. And the next step is the data preparation step. And in fact, in the data preparation step, you just have to apply everything that was written. And so here I'm doing the data preparation. I will not do everything that we have said because I want to keep some biases in my model at the end. So I have created a scikit-learn pipeline, and I'm just doing the bare minimum to have something that is usable after that. So I have a lot of code to do that. I have my column transformer, I have the column names, and I split the train test between the X and the Y, the important inputs I will have and the output I will have to predict. After that, I'm doing the modeling step. So the modeling step is where you are creating a lot of models and trying to find the best ones. Here, I will create 2 very complicated models, a tree, a decision tree, with 3 or 4 levels, and another tree that is a bit more complicated because I have a max depth of 10 instead of 3. So of course, I'm using only very simple models here because I don't want them to be too powerful and to find too many things to show you some biases. But you can do what we will do with any kind of models and not only with trees, of course. So we are doing the training for the small tree and the big tree. So the small tree is max depth 3 and the big tree is max depth 10. And I do a classification report to see if my model is correct. I've got a very high accuracy of 92%, but remember that 91 is just saying that no one is ill. So it's not that good, 92. And what is interesting is to detect people with heart disease or with a high risk of heart disease. And here my recall is very low with only 4%. So my model is not good at all. This kind of model, you will not keep them, you will just throw them away, but here we will study it just to understand what you can do with it. And if I look at the big tree, it is way better. The accuracy is a bit less, 73%, but I have 79% of recall, so I detect nearly 80% of the ill people. So this model is way better, and it is a good one for this kind of applications. And so we will go to the last step, the evaluation step, and the evaluation step is the last step of my iterative process, and the last one where I can spot biases. Because maybe you have not seen some biases in the data set at first, and now you will have to look at the model to know if there are biases in your model. And of course, you cannot just open the model and look at it. Most of the time, you will not understand the model because there is something between interpretability and accuracy. The more powerful is a model, the less interpretable it is. For example, neural network, you cannot understand that is inside a neural network. And so you will use Explainable AI to do that. So Explainable AI, there's a lot of XAI algorithm that you can use. You will find them on the internet. I've just put some of them here. They can be local or global. a local model is working for one data point and saying why, for this specific person, you have said he will or will not have a heart disease. A global algorithm will work for the whole population, saying what are the main risk factors for the population. It is not the same to say what is important for one person or for the whole population. There are another classification between specific and agnostic. Specific algorithms are working only for one type of models, and agnostic are working for every model that you can find. And so we will use some of them. For example, you can use feature importances. It is specific only for decision tree or algorithm based on tree, and it is global for the whole population. And you can have what is important for your model. For example, for my small tree, I can see that half of the decision is based on general health. And then the second feature is having a stroke before the diagnostic. And the third one is that you are 18 years old or over. Okay, so you have these kind of things. For the big decision tree, of course, I will have more features with a bit less importance, but what you can see is that the first ones are the same than for the small tree, the gen health, 18 and overs, and a stroke, a previous stroke. So you can be rather confident that these three features are important. You can also do something specific and local this time. It is just reading the tree. If I use the patient number 3, which is this one, I can know why I will say it is someone with a high risk or not of heart disease, just by looking at the tree. Of course, I can do that only with the small tree, because the big tree is too big to be printed. But here you can just look at the decision tree. And so if you look at the people, you have the whole preparation step to have every information. I will go from the root node. The gen health is very good, so I will go to the right. Then the person has no stroke, so I will go to the left. And then it is someone who is 50, 54 years old, so I will go to the left. And I found the leaf, which is saying that the class is no. I will say that this person has no heart disease, okay? Donc, of course, you can do a lot of things to verify that, and it is very easy to do that, to do something specific. So we have seen two specific algorithms. You can have agnostic one. For example, you can use LIME. LIME is local interpretable model agnostic explanations. It is agnostic. It is working for every model. The goal is just to take your model, to take the data point you're trying to explain, to change it a bit, and so to create a new data set. The new data set is your data point and slightly different versions of your data point with the corresponding outputs. And then you have this data set. You are creating a very simple algorithm, something like linear regression or a small decision tree, and then you will look at this model to understand what is happening. And so here, I'm trying to do that for the same third patient, and I see that what was important to say no, it was because the person has no stroke, was younger than 80 years old, and that the general health was good. It was under 2. And in fact, it is really what we have in the tree. So it's very good here. We have found exactly what was in the tree. If I ask too many features, I will find things that are not in the tree and not useful. So be careful with LIME. Do not ask for too many features, because there will be a lot of noise in the last features. For example, if I ask 6 of them, I have 3 features with nothing interesting in them. I can do the same with people with yes instead of no. And of course, you can do that with every model that you can find. Another thing that I like a lot and it will be the last thing I will show you in this demo, is the subpopulation analysis. It is agnostic, it is global. The goal is just to find if your model is working for every class in the same way. So it is exactly the definition of a bias or not. You will look at every group of people in your data set and see if the model is correct or not. So here I have used the race feature, and so I've done just classification reports, but for every race that I have in my data set. On my small tree, I can see here the result for the American Indian, Alaskan Native, for the Asian, for the black people, Hispanic, other, and white people at the end. And what I can see is that the recall, which is very important for me, is between 4% and 8% here. So, of course, it is from 1 to 2. But in fact, it is very low in all the cases. So there's not a big bias in this model. But if I do the same with my big tree, I will have these results. And as you can see here, for the Asian people, the recall is only 58. But if I look at the white people, the recall is 81%. So I've gone from 50 to 80% of recall regarding the race of my patient. And this is a big racist bias. I didn't mean my algorithm to be, my model to be racist, but I have a racist model here. And I can find that with subpopulation analysis, okay? So do a lot of XAI algorithm to find the most biases that you may have in your models after that. And to finish, I will go back to the slides. So I had a button with a tag demo, and now I have another button for with a tag PC, so it is very easy to find it. So to conclude, what is important? First, biases don't come from the data scientists, they come from the data set. Okay? It's very important to understand that. So, analyze the data set by asking yourself a lot of questions, and a lot is very important. Don't do something very quickly, just saying, oh, okay, it will be okay, oh, it seems to be correct, yes, and don't pass the data understanding step. 3, use multiple explainable AI algorithms. Not one, not 2. Use a lot of them to understand really how your model is working. And the last one is no tool will do that for you. Of course, tools can say, there's something strange here, but it will not say if it is some normal thing or if it is a big, dangerous thing that is happening. And so you will always have to use human intelligence to do artificial intelligence. Of course, it will take a lot of time, but if you are in some minorities population, like I am, because I'm a woman, you will be very pleased that someone has looked at the model and say, okay, there are no biases in that. Okay, so please do that in your models. Be aware that there may be some biases. Be careful with that. You have the QR code at the end also if you want to download the notebook. You will have it in the slides, so no problem for that. I say thank you to all of you. Thank you for this moment on stage with you. I hope you will have a very nice week during this reInvent. Don't forget to answer the survey. It's very important for me to know what was good and what was not that good to be better next time, and for AWS to show you very good conferences in the next reInvent. If you want to contact me, you can. You have my email address and you have my LinkedIn page, so don't hesitate. You can send me messages and so on. Maybe I will not answer on the same day, but I will answer one day. Be sure of that. Thank you. Thanks a lot. Have a nice week.